Now, here's an application. Suppose I send W, an integer, turn it into some waveform W, xn, put it through some noisy channel, get yn, and come out with W hat, some guess of what I put in. Then the mutual information between my signal, some would call this a signal, but what I intend to send, and my guess is less than the mutual information between the input and the output. Okay, let's cheat a minute quickly. Suppose the W is uniform over 2 to the NR values. And suppose this is what's called a memoryless channel, in which the current output Y depends only on the current input X. And then, under these conditions, this is equal to summation I, it's less than or equal to summation of I of Xi, Yi. That's because it's a memoryless channel. That takes some proving. And each of these is less than the maximum mutual information over all inputs X, distributions P of X. So this is less than NC. So you immediately have that the relationship of your estimate of what was sent to what was sent, that is I of W hat, is less than N times the channel capacity. So as I said, this part we haven't shown. And it depends on the channel chopping things up, that is being a memoryless channel. All right, now let's look at the notion of sufficient statistics. You know, I know that if I do an experiment over and over again, I only need to keep track of something. For example, a baseball batter comes to bat 1,000 times and he gets 600 hits. I didn't need to know when he got those hits during his 1,000 at-bats. If I make the simple assumption that his at-bats were independent, identically distributed random variables, I'm just trying to estimate his true batting average, the true probability, theta, that he gets a hit. So I've reduced the sequence of ones and zeros, hits and misses, of length 1,000, to just the number of ones in the sequence. So that's the notion of a sufficient statistic. And when does that not lose information? So, sufficient statistics. So we have a family This is a family of probability density functions. An example might be this. X is equal to x1, x2 through xn. And these are Bernoulli theta. And p sub theta of x is nothing more than theta to the summation of xi times 1 minus theta summation of 1 minus xi. So the probability of this precise sequence is this, where the number of thetas in the product is the number of ones, and the number of 1 minus thetas is the number of not ones, that is 0. And we will say definition, T of x is sufficient, is a sufficient statistic with respect to, that is WRT, the family P theta, if theta goes to T goes to X. You say, wait, do you have it wrong? And this is for all distributions on theta. For all, if this is true for all distributions on theta. Note, always have theta to x to t of x. So we'll say a statistic is sufficient if we also, if we have theta goes to the statistic goes to x. Or equivalently, if the unknown parameter theta and the data x are conditionally independent given the statistic t of x, then we'll say t of x is a sufficient statistic. Makes sense, because it just says x has nothing more to say about theta. It means p of theta given t and x depends only on t. Example. Theta goes to t, goes to x. And here, probability t is equal to k. Oh, the example is for the Bernoulli sequence. Theta goes to x1, xn, goes to t of x, equals 1 over n summation of xi. All right, if the probability of t equals k is what's the distribution of the number of heads in n flips of a theta coin? It's just n choose k, theta to the k, 1 minus theta to the n minus k. All right. And now what about x? X in which is a sequence 0, 1 of a length n is uniformly distributed over all x such that summation of xi equals k. And uniformly distributed is 1 over n choose k. Because there are n choose k such sequences having k ones. So I claim we could generate the data this way. We could generate an x we generate from theta, we generate the number of heads, t, and then we pick a random sequence with that number of heads. And it makes sense, because these were IID random variables. The order in which they happen doesn't contribute at all to our knowing the underlying probability distribution. And because of that, x is conditionally independent of theta given t. Mendel, when he did his experiments on blue-eyed peas or whatever they were, he knew that the answer he wanted was 1/4. You mix these two, you get the genetic consequence. 1/4 of the time, 3/4 you don't, so on. So he knew the answer ahead of time. And the problem with his results, looked at in retrospect, is that the proportion of occurrences of this event, say you'd expect 250 out of 1,000, that's a fourth. He might have gotten, say, 260 out of 1,000, or 240 out of 1,000. Which is well within a standard deviation. And he got this over and over, at least according to the sources. And so his results are really too good to be true. Now, there are two ways of your getting results that are too good to be true. One is to pick out your result t ahead of time, and then do the randomization and report that as your data. That's, I'm sure he didn't do that. But the other is to say, is this brown or blue? Well, it looks sort of weedy, and I've been getting too many browns. I'll throw it out, you know. So basically, if you selectively